All right, Jeff, we've got your brass you sent in the different states. This is your case holder you sent in. Looks like may have made contact with the gutter and the IDOD. So first we're going to check the ID and OD concentricity of the case holder. So we'll put that in a V block because that will guarantee we're spinning about the OD. I'll take this indicator I'll put inside there. You can see the indicator is live. And we're going to spin this. As you can see on the thousandths indicator anyways, there's no measurable run out. Let's check the back of it. Let's ring this, make sure this indicator is live. No measurable run out. So now we know the ID and the OD of this case holder is concentric, which it's going to be because it's made all at one time. So it's bored and then turned and then cut off. So it's going to be concentric. So now let's take, this is the brass you sent, Lapua 30BR unturned. So this is with your expanding process. We're just going to check these three. First thing I'm going to do is check the fitment of the case and the case holder. How I do that, just put it in and then I wiggle this front and I wiggle this back and then I put this in backwards. So I've got no wiggle, which means the taper is correct, and you can see how far it's hanging out. If I put it in backwards, it's contacting there, which means it's the exact same taper as this case throughout the whole distance of the body. So that's good. That's what we want. Now we're going to move on to checking run out here. Move this up. Okay. So what we're going to do is I'm going to put that some magnets to keep it in one distance. So you can see there's the apex of it. So now I'm going to turn this. So already right there, what do we see? 3.5 thousandths. That's one above. So if we, that's 2.5. So we got 1, 2, 2.5 thousandths there. Okay, now let's go to the back of the case. If you look here, we've got almost half the distance, right? So if we go in the middle, you see how much run out we've got. Go in the end, see how much run out we got. Now we're going to go down and check the ID, because as we all know, after expanding, the ID and the OD is not the same thickness congruency all the way around. See that run out there? That's in the front. Now we're going to go back a little. So you can see they're not the thousandths that, you know, you thought they were when you measure them. And how I'm doing this is how we do an inspection in the machine shop. So this is basically the least amount of error you can have for, you know, considerable reasons. You know, there's no bearings that are going to give you additional run out. We're spinning about one axis. So we're going to go ahead and check this one. Oop, hold that there. So this one, as you can see, it's much better, right? Okay, let's check about halfway back. Look at that. We're twice as bad there as we were here. You see that? Here's our thousandths. Let's go halfway up the neck. Look at that. 2 thousandths. Now let's go back. See that? Now let's check this third piece of brass. Ooh. So we've got 0.003 there. Two and a half. That's 0.003 nearly of run out there. Let's check back here. Look back here. It's pretty good, right? Now let's check out the tip. Ooh. Ooh. Man, it's pretty bad. So I know you said these had 1,000th run out. As you can see, that's not the case. And it may be the case at one point, but it's not the case throughout the whole length of the neck. And if we go down here, I'm gonna put this on the ID. I need to let me keep this held there. See how much run out there is on the ID? Over 0.003. So this is where the problem comes in, because from what I know and what you said, this brass is starting out as expanded at like 10.8, 10.9, you know, 0.0108, 10 thousandths and 8 tenths. Okay, you're turning it to 10 thousandths 3 tenths. That's 5 tenths of a difference. It's physically impossible to ever get cleanup on this brass, how it's expanded, unless you're going to take off minimum 3 thousandths of neck wall thickness from the highest to the lowest point. Okay, so the way to fix that is to run it in, you know, traditionally how we do it, I've shown in other videos, is in our die to expand it and then force the body and the neck to become back concentric. So this is some 30 BR Peterson you sent. Let's check this. I'll kind of do it quicker since we already went over the basics of everything. Check that fitment. It's a little bit smaller, but the taper is consistent, which is good. So we're going to come here. Bring that from the height gauge. So as you can see here, hold that, spin that. There, it works better that way. So unless you're going to take off the amount of run out it has, it will never clean up inside and outside. And this is made very clear in all the documentation for the iDot and AutoDot, and actually on the order form that you signed when you ordered the machine. So this here, you can see way more than 1,000ths there, way more than 1,000ths there, and way more than 1,000ths there. So I haven't seen any of this brass that's less than 1,000ths throughout the whole length. It's another piece. So this is a problem why you're not getting cleanup, and it's simple physics, right? I mean, whoa, look at that. Ooh, 4,000ths. If this neck is wobbling that amount, you have to have the cutters be thin enough to take that amount out of the inside and outside, and that will make it clean up. That's why you didn't clean up here. And let me show you something that's evident on backing what we've seen. Usually the very back of the case is better run out than the very end. That's because it's projected. See how you fully cleaned up here, but not here? That's because that run out's projected. Same thing here, same thing here. Same thing in these ones. So as you can see, the problem is you're spinning about this axis and the spindle of the iDot or AutoDot doing the same thing it's doing here. And you cannot get full cleanup unless you have less run out than the material thickness you're removing from the wall.